Hi everyone, today we are going to learn more about one of the most common ML algorithms, which is linear regression, and we are going to go through some of the basic concepts needed for linear regression and how we would use that to predict values and find patterns within our datasets. So first of all, what is linear regression? It's basically an algorithm which predicts continuous values. So we want to use it to predict continuous values, and it has a constant slope. Now what we mean by a constant slope is, let's imagine on a 2D plane we have some data points. It can be anywhere on the 2D plane, and then we have a slope, creates a line that fits our data points. So this line is a general representation of the pattern within our data points, and the slope, because it's linear, we say we will always have a constant slope in linear regression, and this usually maps continuous values. So what we mean by continuous values is they need to be in a range, let's say from our input data set has a range of 20 to, let's say, 120 within a data set. So we will our output would also have a number between 20 to 120. So that's what we mean by it predicts continuous values and it has a constant slope. Now let's go further into linear regression. We said linear regression, or at least simple linear regression, is defined by this function, which is y equals to mx plus c, and you might have seen this in your calculus classes. Here m is basically the slope of the function and c is the constant bias of the function. Now in machine learning, bias usually means that there is some residual constant that we add to the function. Let's say if x is our feature and y is our label, then what we mean is basically if all of our features are put to a value of 0, does that also mean that our label, or actually this is just the output or the outcome of our function, does it also mean that our function output has to be 0? And it's not necessarily true. Let me give you an example. Okay, so let's take an example here. Let's say y equal to salary of a person and x equals to their years of experience. So here what we have is x as the feature and y is the output label that we want to predict. Now we have this bias term because, let's say, if for some of our data points, if we put x to 0, let's say, one of the person that we're looking at has no experience, no corporate experience, does that also mean that y, which is our salary, should also be 0? In this case it won't be, or actually in most cases it won't be, because we factor in a constant term, which is something like a base or minimum salary for a role that we incorporate into the function. So our function, even though our features, or let's say the years of experience here, is 0, the output will not be 0, rather it would be a constant for let's say a given industry. It will be a constant for people with no years of experience. So this is what we refer to when we say constant. So a simple linear regression, to sum it up, has a function of y equals to mx plus c, where c is the bias term or the constant and m is the slope. Now there are a couple of factors when we consider linear regression as an algorithm. First is, how do we understand the performance of this algorithm? We need the cost function to tell us how our model is actually performing at a given point. And what the cost function tells us is how much does the true value differ from the predicted value. So this is basically the difference between the true value minus the predicted value. And this is what a cost function basically does. Now the true value is the label that we already have from the data set, and this is the predicted value that we get from the model. The true value is something we would already have within our data set, because this is a supervised ML algorithm. If you want to know more about supervised versus unsupervised ML algorithms, you can check out my other video where I brief you more on these topics. But basically, because this is a supervised ML algorithm, we already have our labels, and that will be our true value. Now the predicted value is what we get from the model by giving the model just the features and then getting the output as the prediction that we get from it. So that's our cost function, and some of the properties of the cost function are, it's used to measure the performance on training data. And why I say training data is because we use separate metrics to test the performance of the model on the test data set, something which the model does not see while training. So we compute statistics, we compute the parameters of the model, such as weights and other things, coefficients for linear regression, and we compute these parameters during the training of the model. And to check the performance of the model during training, we use the cost function. And usually we use metrics or measures like mean square error, especially for continuous variables, such as in linear regression we will use mean square error, which is basically the sum of the square of the difference between the values. So this is the difference between the actual value and the predicted value, and then we square them and we take the sum from I equal to 1 to n don't be scared of this notation. It's basically just saying, you take the sum, or rather sum all data points from I to n. So you just take the sum of all values, and then you divide it by the number of data points, or the number of values, because that will give you the average mean square error. And this is what we use as the cost function. And it's a popular cost function for linear regression. And well, there are some nuances to or comparisons between the cost function and the performance metrics on the test data. For example, accuracy is actually a percentage. It calculates the accuracy across all data points, which outputs a percentage of the truly predicted data points. But this is a performance metric we'll check later. But basically, the mean square error is not a percentage, it's rather a number. So it will give you like a number which does not represent a percentage of the entire data set. That's just a small difference I wanted to note here. But basically, now that we know about the cost function, we'll go more into how we optimize a model based on this cost function. So first of all, you need to know the parameters of this function. This is our function for linear regression. And I want you to pay attention on the variables here. So C is a constant, it's just a bias that we add. For simple linear regression, our only variable is the slope. And basically, we need to get optimal values of the bias and slope, because these are both the things that can change the predictions of our model. And initially, we just start with randomized values of these variables. So M and C have randomized values. And then we want to update in a way where we get closer to the true values of these M and C for our data set. So each data set will have unique values of slope M and bias C. So for our data set, we want to find the true value, or at least close to the true value of slope and bias. And for that, we use something known as gradient descent. Now, you must have heard about this, especially if you're familiar with machine learning terms. This is basically an optimization method for ML models. And it's a pretty powerful optimization method. Basically, in very high terms, what it does is, you remember the cost function? It takes the partial derivative of this cost function with respect to its variables or weights. Basically, here it's going to take the derivative with respect to m and c. In our case, for linear regression, we need to optimize for m and c, which is why we're taking the partial derivative for both of these variables. And gradient descent basically takes this cost function and calculates the partial derivative, right? And let's say our cost function is something like this. So this is a 2D plane, this is our cost function, what gradient descent does visually is first we initialize a random point for these m and c values, which is slope and bias, right? Gradient descent gets the slope of this function in a way where it gives us a direction of the optimization. So gradient is actually a slope with respect to this point, and gradient usually gives us the steep or the ascent. What we want to do is go in the opposite direction, because remember, this is our cost function and we want to minimize our cost function. To minimize our cost function, we want to go down and get to this point. This is our optimal point. Just gonna mark it with orange because this is our optimal point. We want to reach here. Initially, we start with a point which is here, and when we calculate the gradient descent at this point, it will give us something that goes down in this direction. And then once we come here, this is the new point that we get, which is, let's say, M2 and C2. These are the values we get after one step of gradient descent. We want to continue doing this till we get to the optimal point. So again, at this point, we calculate its gradient, and the gradient here will be something like this. We want to calculate the gradient at this point again, and so this point will give us a gradient, and the slope will be this, and we want to go down in the opposite direction, so this will be our gradient descent. And basically we continue doing that till we come down at the optimal point. Now we get the direction by gradient descent. Hope you've understood the concept behind gradient descent. Gradient descent basically gives us the direction of the update. And it tells us which way will lead us to the optimal value for this function, which is basically to minimize the cost. But what actually determines the value that we subtract from our current point or add to our current point is the learning rate. Now, learning rate is a hyperparameter, which basically means we can tune it. It's something that we decide while building a model. And what it does basically is, let's say we give it a value of 0.2. This learning rate tells us how much will we update our weights. And by how much, I mean it controls the size of the weight updates. So what it does is basically controls the size of the weight update, where we get the update, the actual update from gradient descent. So let's say we get this from gradient descent, but the size is what we get from the learning rate. So basically, gradient descent plus learning rate gives us the update of our variables or parameters. And this is exactly how we update our cost function. So let's say on a high level overview, I'm going to summarize this, is we have our cost function, right? Initially we have a set of randomly initialized weights, and by weights what I mean is for our slope m and c bias for a linear regression function, but in general we'll call it weights. So the cost function has initially a randomly set of weights, and how we optimize this is by going through the process of gradient descent, which is basically calculating the gradients and calculating the opposite direction of the gradient, plus the learning rate, which will give us the size of the optimal update at that given point, and then we update the parameters or the weights and compute the cost again. And basically we keep doing this part, which is basically compute the cost, and this part where we update or optimize the weight. At a given point, we keep doing both of these steps till we are satisfied with the result of our model, which is basically till we are satisfied with the predictions it's making. So for example, if we say our given example was, if y is the salary and x is their years of experience, we want the model to perform at a level where if we just give the salary of our person, which is the x, it should give us a reasonable prediction. Sorry, if x is the years of experience, it should give us a reasonable salary corresponding to that years of experience in a given domain. And this is obviously domain specific, and our data set would also be domain specific. But within a domain, if we have a new data point, which is the years of experience of any given employee or person, we should be able to reasonably predict their salary for a given role. And that's basically everything that we need to know about linear regression, at least simple linear regression. So I have a small note for multivariable regression, which is also linear regression, but basically this is a little different from simple regression. So actually, let's go one step back. I just want to give you a high-level overview before we go into that. So within linear regression, we have simple regression, and then we have multivariable regression. Now, the only difference between these two is exactly what the name suggests. One is a single or at least a simple variable version of the other. So in simple regression, we assume the function has a form of y equals to mx plus c, where we only have one feature and we need to predict the continuous variable, which is our output. This is our input, and we need to find the optimal values of slope and bias. And these are the requirements and features of simple regression. Now, for multivariable regression, we are assuming multiple variables in the function. So we have y equals to m1x1 plus m2x2 plus mnxn, basically goes up to mnxn plus c. Now here it's the same concept basically, but here x1, x2, xn, basically from x1, x2 going all the way to xn, these are basically a set of features. So you see how in simple regression we have one feature, whereas in multivariable regression we have multiple features or multiple variables, which is basically what the name suggests, right? And these set of features is something we are already giving to the model. So our data set has multiple features which we give to a model, and then we expect the model to give us a prediction from these given set of features. So that is our y, which will be our prediction, same as the simple regression. And the difference is in calculating our slopes. So we will have m1, m2, mn. These are our slopes, and then our c is the same as bias. So basically everything that we just discussed in simple regression is the same as in multivariable regression, including we can have a similar cost function. We will also apply gradient descent. We also need to set the learning rate to optimize the weights and then decrease our cost, and basically that will get us to a point where we get an optimal values of slope and bias that will give us the minimum cost. It's exactly the same concept. The only difference is multivariable regression has multiple features and multiple variables that contributes to making a prediction within the model. So the only separate procedure or function we want to do for multivariable regression is because we have a larger number of features, and because all of these features can have different range of values. Basically, we want to make sure that these different range of values does not impact the learning process in a biased way, or the numeric values of these different ranges of features does not directly impact how much the model gives importance to any one feature. And for that, we need to basically have a process called normalization. And although it sounds fancy, what it means is just given any feature, you want to convert this to a specified set of range. So let's say we have features, we have different features, and one of the features has values of 1, 2, 3 and goes all the way till 10. This is just gonna put bar here so we know this is for multi-variable. Let's say this is for feature 1. For feature 2, we can have a range of like 100, 200, goes all the way to 1000, and then we have feature 3 that just goes from 0.01, 0.02, and so on all the way to 0.08. Now we see the huge difference in the range of these features, right? So we don't want the model to be biased towards feature 2 just because it has a higher numeric value within its features. It doesn't mean that feature 2 is necessarily important for our model to learn the pattern. It doesn't mean that our output is impacted or is favored more by feature 2. It just means it has a higher numeric value, which is why we want to make sure we don't make this mistake of biasing towards a given feature. And so what normalization basically does is it takes all the values of a given feature and converts it to a specified range, let's say from 0 to 1, or another popular range is -1 to 1. And let's consider 0 to 1 for now. So for our feature 1, basically we will have for all of our features, basically we will have a range between 0 to 1. So we will have all of these numbers from 0 to 10 mapped to a range between 0 to 1, and that will be the same. Basically the range between 100 to 1000 will be mapped to 0 to 1, and the same for the lower values as well. Now you see, once we have all features normalized to 0 to 1, we can make a fair comparison between the actual impact of these features on our output variable, which is the salary in our case, and we're able to see that how these features actually impact, or how these features correlate to our output variable, and then our model learns and understands those patterns between them. So normalization in multivariable regression is important because it helps you scale all features to the same range, and same range is very important for our model to learn accurate correlations or accurate patterns between these features and the output variable. And there are a couple of ways you can do this. You can basically divide features by mean value. That's one way to normalize our features. Or the second option is to divide it by the range. Actually, sorry, I think we need to subtract it by the mean. And the second option is to divide feature values by the range of a feature. And what I mean by the range is basically its max value minus its min value. So this is the range of any feature. You get the range by subtracting the max value by its min value, and then you can divide all features by this range, and that will give you all values between 0 to 1. Or you can also choose option 1, where you can take the mean and then subtract all features by the mean value. So basically this is normalization, and it is recommended you do that before you start the training for multivariable regression. And it's multivariable regression is very similar after the normalization. It's actually the same as simple regression that we discussed in detail. I'm giving you a high-level overview. What we discussed is the cost function, the gradient descent, and the learning rate. So I'll summarize that. Linear regression has a few components. One is the cost function. Second is how we optimize or get a lower cost from this cost function, and we do that by calculating the gradients, by going through gradient descent, and then choosing a learning rate that will give us the size of these updates. And we basically take a better value of these variables, which is our slope, and constant, which is our bias. We update that to our cost function, we calculate the cost, and then we keep doing that in repeat till we get either a satisfactory error for our model, or we come to a level where the error is no longer decreasing. So if we come to, let's say after a few iterations, we come to a stagnant error across multiple iterations, or we get a satisfactory error, or basically performance of a model is when we stop the training process, or we stop the learning for our algorithm. And that is linear regression summarized in a page. Let me know if you want to understand any of these topics in further detail, and I'll be happy to create a summary or an in-depth understanding of the topic. And thanks for watching. Hope to see you next time soon.